Welcome to another TIFR problem solving session. So today's problem, as you can see, it states that there exists no monotone function from R to R which is discontinuous at every rational number. Is it true or false? So it's a bit constructive proof, but let's think about it. All right. So suppose I define a function from R to R like this, goes to summation over qn less than equals to x 1 by 2 to the power n. So why am I able to define this function? I'm able to define this function because of q is countable. So since q is countable, what does that imply? It implies that I always have an enumeration of q. Since q is countable, it always has a set theoretic bijection with natural numbers. Right? So that's why there is always this enumeration, like the first rational number, second, third, and it goes on and so on and so forth. So this function that we have actually defined, so this function is well defined. All right. So this function is well defined. One of the reasons is that this series is absolutely convergent. Okay. So how is it actually defined? So the series is 1 by 2 plus 1 by 2 squared. So for the first rational, it is 1 by 2. For the second rational, 1 by 2 squared plus dot 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 till I reach x. Whatever the rationals I have, I am getting 1 by 2 to the power n. Okay, so for the nth rational, I will have 1 by 2 to the power n. So this function is well defined because the series is absolutely convergent. So now the point is, if you look at it, I need to make it a monotone function. Okay, so that is one of the requirements, that I need to make it a monotone function. So how do I make it a monotone function? We don't have to make it a monotone function. It is an monotonically increasing function. The reason is, let's say if I take x less than y, so then there exists some q in this x comma y open interval, right? Is a rational number. A q is rational, so it will always be inside this open interval. But the moment it is always inside the open interval, what is f of x? So your f of x is this summation all such qn less than equals to x 1 by 2 to the power n, but f of y is all of these. So f of y is practically all of this plus 1 by 2 to the power n. Okay, because see, after x you are taking q. Okay, so it is f of y is at least this much. That means f of y is practically greater than or equals to this, which practically implies that f of y is greater than or equals to f of x. Okay, because since you have a rational number after x, for that you are going to get that 1 by 2 to the power n. Okay, so that is why it is becoming a monotonically increasing function. So this is the reason that this function becomes monotonically increasing. Now the point is, will it be discontinuous at every rational number? So now we need to check that is f discontinuous at every rational. So it's a function from R to R. So when it is continuous at a point, whenever I have limit x tends to x naught, f of x equals to f of x naught. Okay. So this is precisely when it happens. So that means what? That means limit x tends to x naught plus f of x and limit x tends to x naught minus f of x, they're both equals to f of x naught. Okay, so this is the definition of continuity, continuous functions in R. So now, but if you take this, given our function, if you take limit x tends to qn minus, so this is what f of x. So this is precisely collection of all such rationals that is strictly less than qn by 1 by 2 to the power k according to their enumeration. But what is my f of qn? My f of qn is summation of qk less than or equals to qn by 1 by 2 to the 1 by 2 to the power k. So this less than equals to sign makes a huge difference, because the moment you have less than equals to sign here, then this summation becomes larger than this summation, and thus we find that limit x tends to qn minus f of x is not equals to f of qn. And hence, what did we do in the process? We constructed, so let's say, thus f is a monotonically increasing function that is discontinuous at every ration. Okay, so it becomes false. All right, so that there exists no monotone function which is discontinuous at every rational number. So we constructed a monotone function that is discontinuous at every rational number. So the idea behind that was this: how to construct this function with the help of the enumeration of the rational numbers. And the monotonically increasingness was immediate, and the discontinuity was just a very basic limit checking. Okay, so that's it for today. This answer, this true false question is false. So we will meet with another problem from TIFR next time. Thank you for joining.